Welcome! If you have seen my video about rotary encoders and Arduinos, you probably know that I'm not a fan of software debouncing switch contacts. I like to hardware debounce them. The circuitry I described in that video is actually quite simple. For each switch in a rotary encoder, you got a pull-up resistor and an RC low-pass filter. And that is enough to hardware debounce rotary encoders of reasonable quality that contain switches of reasonable quality. For how rotary encoders work in general, how I arrived at that circuitry and the Arduino software side of things, see the aforementioned video, card here, link in the description. So, to hardware debounce a rotary encoder with 3 internal switches, 2 for the rotation and 1 push button switch, you need 6 resistors and 3 capacitors. That's all. But what if you have 2 rotary encoders with push-button switches? Then you need 12 resistors, 6 capacitors, 18 parts in total, 36 pins. That's a bit much. What if I told you we can do the whole shebang with just 2 parts and half the number of pins? Enter the MC14490, a hex contact bounce eliminator. And it just requires only 1 external capacitor to work. And it has a lot of features, just the 4 most important for us. Of course, it can debounce 6 switches. It has internal pull-ups on the inputs, so we don't need any external pull-up resistors. It does not require double throw switches. Your simple on-off single-throw switches are sufficient, and the supply voltage range is from 3 to 18 volts. And that's the pin out of the little bugger. VDD goes to your positive supply, VSS to ground. Then we have 1, 2, 3, 4, 5, 6 inputs and 1, 2, 3, 4, 5, 6 outputs. And these oscillator pins, that's where the capacitor goes because it has a built-in oscillator. More on that down below. In the block diagram, you find that internal oscillator, which frequency is determined by the external capacitor, and 6 identical debouncing stages. Each stage has at its core a 4-bit static shift register, which is of course driven by the oscillator, and you see the pull-up resistor here for the input. More on how that works further down. Theory of operation is covered by a whole page in small print. I'll try to give you a simplified and short version. Thanks to that shift register, it can remember the history of the input signal. And only if the input signal stays stable for a certain number of clock cycles, the output signal will change accordingly. And this will happen within 3.5 and 4.5 clock cycles. Of course, they provide you with a formula to calculate the oscillator frequency, and please note the external capacitor has to be at least 100 picofarad. We will use the formula in a moment. And if you ever see a star in a datasheet, follow the star, and that leads us to power down consideration. What that chapter says is basically when you switch off the power supply to the chip, the energy stored in that capacitor might, under some circumstances, damage its internal circuitry. And they give you here a formula, turn off time of the power supply must not be faster than T, your supply voltage times the external capacity divided by 10 milliamps. And of course we will check that after we've calculated the size of our capacitor. Now it's finally time for some breadboard stuff. The Arduino is just supplying a 5-volt rail here and ground rail to the breadboard. In itself, it's powered by that USB power bank. My rotary encoders have all a ground connection here for all contacts, and for that encoder I added a 10K pull-up resistor for one contact, and I'm measuring here with the oscilloscope what's going on there. The oscillator in our debouncing chip has to run fast enough so that it can still recognize the fastest on-off on cycles of our switch. Remember, it needs about at maximum 4.5 clock cycles to pass the signal through, but it has to be slow enough to filter out any bouncing in our signal. So let me try to do a signal capture of a very fast turn. I did my best to turn the rotary encoder as fast as I could, and yeah, that's the result. Just one increment signal from the encoder, and it's about 3 milliseconds. Now let's zoom in at the edges and have a look at the bouncing. The bouncing at the falling edge is over after about 25 microseconds. The bouncing on the rising edge went on for about 50 microseconds. Let's have a look at some other pulses from the switch. Ooh, we have bouncing at that falling edge for about 100 microseconds. Let's move further down the signal. About 75 microseconds for the next falling one. In between a bounce-free rising edge. Another 100 microsecond one at a falling edge. And that's it. I scanned through all the other rising and falling edges, and the longest bounce time was 100 microseconds. The fastest on-off switch time I measured was 3 milliseconds and the longest bounce time 100 microseconds. Of course, we could have had a look into the datasheet of the rotary encoders. I've got some Born's PEC12Rs on my breadboard, and there in the datasheet it says contact bounce at 15 RPM, 2.0 milliseconds maximum. And RPM operating 100 maximum. If you take that number, so 60 seconds divided by 100 RPMs times 24 positions per rotation, you get a minimum signal period of 25 milliseconds. We only measured the downtime of the signal, so 25 milliseconds divided by 2 gives us 12.5 milliseconds. I reached 3 milliseconds, so I over-revved them considerably. Anyway, that leaves me between the devil and the deep blue sea. Do I go with the 3 millisecond measured or the 12.5 milliseconds specified for the minimal frequency? If we say, it was between 3.5 and 4.5 clock cycles, let's say 5 clock cycles, that gives me for my 3 milliseconds, 5 clock cycles divided by 3 milliseconds, a minimum frequency of 1.67 kilohertz. And for the value from the specification, 5 clock cycles divided by 12.5 milliseconds, 400 hertz. It doesn't look better when we look at the bounce times. I measured a maximum of 100 microseconds. Burn specifies 2 milliseconds. I guess they're just trying to save their behind. But just as to give you an indication of the maximum frequency, 1 divided by 100 microseconds is maximum frequency 10 kilohertz for our chip, and 1 divided by 2 microseconds 500 hertz. And this is really just an indication. Because I gave you a really short version of the principle of operation. That chip doesn't simply shift in the level at the input into the shift register, which each clock cycle. It does much more, and it uses 2 phase-shifted clock signals. Okay, so maximum frequency we calculated there, really just an indication. And then we have, of course, the technical maximum of the frequency, which is given, yeah, you remember the formula, for 5 volts, the frequency is 1.5 divided by the external capacitor in microfarad, which is given by the minimum capacity of the external microfarad of 100 picofarad. So 1.5 divided by 100 pico gives us, with that formula, 15 kilohertz. So here I calculated by just rearranging that formula. So our external capacitor in microfarad is equal to 1.5 divided by the frequency we want. I've calculated all possible capacitor values for 400 Hertz, 1.67 kilohertz, 10 kilohertz, 500 kilohertz. So that ranges between 150 picofarads and 3.75 nanofarads. And I decided we start with a 1 nanofarad capacitor because that's what I got in my drawer. It's alive! No, seriously, I just put the chip on the breadboard, connected VDD to the 5-volt rail of the Arduino and VSS to Arduino ground, and put that 1 nanofarad capacitor between the oscillator in and out pin. And measuring across the pins of that capacitor with the oscilloscope, I can see the oscillator working at 1.25 kilohertz, which is totally okay because the data sheet states, yeah, formula plus minus 15%, and the capacitor is also plus minus 20%. But what a crude oscillator they have implemented. Doesn't matter. It's just driving the shift register and some other internal logic. Of course, it cannot only oscillate, it can hopefully also debounce. And yeah, it does. Nothing much changed on the breadboard. I've just connected that one contact that was previously pulled up to 5 volt now to the input of one debouncer in the chip and also to an oscilloscope probe. And the output of the debouncer is connected to another oscilloscope probe. I've just single captured one of those pulse trains from turning the rotary encoder. Yellow is the input and blue is the output. And as you can see, we have that promised delay of 3.5 to 4.5 clock cycles between input and output. Now let's zoom in on the edges and see if it's really debouncing. And indeed it does. Here the falling edge from our rotary encoder with bouncing. Here the delayed falling edge out of our debouncer. Absolutely clean. Rising edge of the input with some bouncing. Rising edge of the output. Delayed but without bouncing. Now here I have a falling edge with terrible bouncing, but yeah, no problem at all. And a terribly bouncing rising edge, no problemo. I promised you we would check the power supply turn-off time constraint in conjunction with a capacitor size in the power consideration chapter here after we've chosen a capacitor. So let's do that now. Here's the formula from the datasheet. So T is equal to VDD minus VSS, so basically our supply voltage, times the capacity of the capacitor divided by 10 milliamps, so 5 volt times, 1 nanofarad divided by 10 milliamps, and that's 0.5 microseconds. You would be hard-pressed to find any power supply that can shut down completely to 0 volts within 0.5 microseconds. So we are safe, but in case our power supply would switch off faster, we would have to add 2 more diodes to protect the chip from being damaged by the charge inside the capacitor. But yeah, we don't need that. I guess it's time now to wire up the other 5 debouncers in that chip, connect everything to the Arduino, and write some code, huh? And of course it works. I just reused the code from the Rotary encoder video. I already carded it, link in the description. And I called the left encoder stroke and the right encoder speed. So if I turn now the stroke encoder, of course you see the value, the relative position is changing, and the push button, yeah, that works too. And the same for the speed encoder on the right. Values changing and push button function. Wonderful. Now let's have a look what's on the breadboard. It's not much on the schematic because the breadboard is a little bit cluttered, and on the code. Well, what did I mean by there's not much on the breadboard, but it's cluttered? Well, I didn't add a single part, but just a lot of jumper wires. So there are 5 additional jumper wires, and I have a total of 6 colors here going from the different contacts of the rotary encoders to the input of the 6 debouncing stages in the chip, and from there they continue with the same color 6 jumper wires to the digital inputs 2 to 7 of my Arduino Every. Unfortunately, the schematic doesn't look any better because the designers of the MC14490, didn't care too much about that. As you can see here, the debouncing units are anti-parallel and slightly diagonal in the chip. So A is from 1 to 15, debouncer B from 14 to 2, C from 3 to 13, and so on. But of course we connected it to ground and to 5 volt, and we have that 1 nano capacitor here between pins 7 and 9, the oscillator pins. Now, without tracing every line here, I will take my hands out of the way for a second so you can take a snapshot. I connected from the left encoder A, B, and 2 to the debouncers A, B, and C. And from the right rotary encoder A, B, and 2 to the debouncers D, E, and F. And consecutively I connected the outputs of the debouncers A, B, C, D, E, F to the digital inputs of the Nano Every, D2, D3, D4, D5, D6, D7. And the Every also, provides the ground rail and the 5 volt rail. I didn't draw every pin, but the pins are drawn on the right side. That should be the USB port. Now I will take my hands out of the way and count a few seconds down. 21, 22, 23. The code is really just copy and paste from the code I've already shown and explained in detail in the Rotary encoder video. Card already was there, link in the description. So I won't explain any of the details here, just walk through real quickly. So I define my 6 input pins for the rotary encoders. I have 4 variables where I store the encoder positions in, and the state of the switch. You saw I implemented a toggle switch function, and these are volatile because I'm using them in interrupts. In the setup, I of course initialize the serial because I'm printing out to the serial monitor of the Arduino. I initialize all my pins as inputs, and I initialize all my volatile variables, the positions to 0 and the switches to false. And then I attach a bunch of interrupt routines to the pins. So to 1 pin of each encoder, the A pin, an interrupt, and to the push button pin also an interrupt. There's not much happening in the loop. I have 4 static variables here which mirror my volatile variables, just with a read at the end, and they are static, so they survive through each entry. Their values survive through each entry in the loop. Then I check if anything has changed between the volatile variables and my static variables, and if that is the case, I update my static variables with the values of the volatile variables, and I print out on the serial port what's happened with serial print. Really nothing to it. And at the end we have all these interrupt service routines here. Stroke encoder interrupt pin A, how that works. I mean, of course it changes either plus plus or minus minus the stroke encoder position. Again, refer to the video about rotary encoders. And also for the encoder interrupt S, switch pin an interrupt routine, stroke encoder switch equals not stroke encoder switch, toggle button function, remember. And then we have the whole thing again, just for the speed encoder. And that's it. That's it. Hardware debouncing with the MC14490. If you want to take away a more theoretical point from the whole exercise, debouncing is really about timescales or different frequencies. The signal from your switch that you want is on a different timescale than the bouncing at the edges, or in other words, the frequency of your switch signal that you want is at a lower frequency than the bouncing, which happens at a much higher frequency. So you're basically doing a low pass filter. And in my rotary encoder video, again, I used RC low pass filters, okay? So there's nothing unusual about tweaking around with some frequencies or time constants of RC elements when you are debouncing. And even when you do software debouncing, you're working with time constants. You say, okay, after nothing changed, when 50 milliseconds are over, I assume that's now the stable signal, or something like that. There are only very, very few, only one comes to mind, debouncer circuits that don't incorporate a time constant in one form or the other. That's it for today. See you next time. Bye.